Hi, I'm Miss Igo. Welcome to my classroom. Today we're going to talk about domain, range, and functions. Let's start with some definitions. The first thing that we need to define is a relation. A relation is any set of ordered pairs. The domain is the set of all first values of the ordered pairs, or the x values. The range is the set of all second values of the ordered pairs, which are the y values. And a function is a relation in which each value in the domain corresponds to exactly one value in the range. This means that when we have sets of ordered pairs or a relation, we can't have an x value pair up with more than one y value. This will make more sense when we start doing some examples. So let's look at some examples dealing with domain, range, and function. Right here is an example of a relation. We have several sets of ordered pairs that are grouped together in a set. And we are told to find the domain and the range of the relation and determine whether each is a function. Well, as we defined earlier, the domain is the first values or the x values in a relation. If you'll notice, in this relation, we have sets of ordered pairs, and we know that they're ordered pairs because they're grouped together by parentheses. But then all of these ordered pairs are grouped together using these braces on the outside, or they're called curly brackets. Sometimes I call them squiggly brackets, but these curly looking brackets are what encloses a set. So anytime we write a set, which could be the domain, the range, or the relation, we're going to enclose it in those curly brackets or squiggly brackets. And the reason why we do this, we don't use parentheses because if we were enclosing just two numbers in a set of parentheses, that would look like an ordered pair. And so we want to differentiate between an ordered pair and a set of numbers. So for the domain, I'm going to start out with the curly bracket, and mine may not look very pretty, but you can tell the difference between that and a regular parenthesis. So the domain would be all of the first numbers in the set, which would be 1, 3, and 5. We have another 5 listed here, but we're not going to put it again in our domain because we're just telling all the different numbers that are included in the domain. So we only need to list each number once. And then our range would be all of the second numbers in the sets, in the ordered pairs, or our y values. And that would be 2, 4, 6, and 8. Well, we defined a function earlier and said that each value in the domain can correspond with only one value in the range. Well, here we have a number in the domain, a 5, that corresponds with the number 6. And then here we have 5 again that corresponds with 8. So 5 corresponds with two different numbers. Because 5 corresponds with two different numbers, or we can say that 5 is repeated. If any number in the domain is repeated, then it is not a function. Here we have another relation. Let's list the numbers in the domain. And that would be 1, -2, 3, and -4. And then the range, all of the second values or all the y values would be 1, 3. We have 1, 3, and then we have another 3, but like I said, we only need to list it once when we're putting it in the domain or the range, and 5. Okay, now we need to determine whether or not this is a function. Well, earlier we had the 5 in our domain, and it corresponded with two different numbers. Well, here we have 3 and 3, but these are members of the range, not the domain. So it's okay if the range is repeated, we just can't have our domain repeated. And our domain doesn't repeat. We have a 1, a -2, a 3, and a -4. Those are all different numbers. The numbers that were repeated, or the numbers that were the same, were the 3's that were in the range. So because our domain is not repeated, each number in our domain goes to a different number in the range, then it is a function. This is just another example of how relations can be represented. This is called a mapping diagram. And what this does is this maps values of the domain to values of the range. And these arrows just show which values are matched up with which values. So here, 2 is matched up with 1, 5 goes to 1, -1 goes to 7, and 3 goes to 7. So what we said earlier when we defined a function was that each value in the domain has to go to a different value in the range. So that means that, for example, 2 can't go to 1 and 7. It can't go to two different y values. But it's okay if we have two different x values going to one y value. If it helps, you can write these out. So if I wrote out 2, 1, that's one ordered pair. 5, 1, that would be another ordered pair. -1, 7, and 3, 20. So as you see, we have the same y values, but we have different, all of the ordered pairs have different x values. So because none of the x values are repeated, we know that it is a function. And then we can list the values of the domain as 2, 5, -1, and 3. And then the values in the range would be 1, 7, and 20. Here's another mapping diagram. And as you can see, we have -3 that is paired up with -4 and 1. So this one x value is paired up with two different y values. So this would not be a function. We still have a domain and a range. Our domain is -3 and 2, and our range is -4, 1, 0. But because one x value is going to two different y values, or again, if I were to list out my ordered pairs, we would have -3, -4, -3, 1, and 2, 0. And as you can see, we have the same x values in more than one ordered pair, so it is not a function. Now we're going to look at some graphs and state the domain and the range, and also determine if the graphs are functions. Okay, so each one of these points on the graph represent an ordered pair. So if I'm going to list out the domain, of course, those will be the x values in my ordered pairs. So I have a -1, a 1, and a 4. And my range would be the y values. So my y value here and here are both -3. And then my y value in this point is 0. So when I look at all three of these values, I have different x values. I have -1, 1, and 4. And remember, that's what matters when we're determining whether or not it's a function. It has to have different x values. It can't have the same x value in order for it to be a function. So because we have all different x values, this is a function. Here we have a line. So when we're describing our domain, we don't have separate points. Every one of these points on the line, and it's not just whole numbers, it would be all of the decimals and fractions in between those whole numbers, would be part of the domain. So the only way that we can represent our domain would be as an interval. And so our domain, if you'll notice, there's arrows at the ends of this line, which means they keep going. And so if we're looking at our x-axis, how far does our line go to the left? Well, since there's an arrow, it's going to continue going to the left forever, which would be negative infinity. So our line starts, or our domain, which is our x values, start at negative infinity. And then as we travel on our x-axis to the right, our line continues to go to the right towards positive infinity. Our range would be our y values, which go up and down. And so if we describe our range, our line continues to go down as we go towards negative infinity. So we would start at negative infinity for our range. And then as we go up, our line continues to rise. So it also goes to positive infinity. Now, to determine if this is a function, remember this means that we can't have the same x value for more than one y value. So if I were to look at any point on this graph, this x value doesn't match up. It only matches up with this one y value. This x value only matches up with this one y value. Every one of these x values only match up with one y value. So this would be a function. Now, another way to look at a graph and determine whether or not it's a function is by the vertical line test. So if you'll remember, a vertical line is a line that goes this direction. My line is not really straight, but pretend like it's straight. If I had a line going this direction, that would be a horizontal line. So we don't need a horizontal line. We are going to be dealing with a vertical line. And so what the vertical line test tells us is that if we were to take a vertical line and pass it across the graph, if it touches our graph in more than one point at a time, then it's not a function. Well, I don't have a line that I can drag, but if I were to take this line and I were to drag it along this graph, if you'll notice, it only touches the line in one spot at a time. It doesn't touch the line in more than one spot at a time. So because my vertical lines will only touch the graph in one spot at a time, this would be considered a function. Let's look at another one so you can see the difference. Okay, so this graph, if I were to take a vertical line and drag it across the graph, as you'll notice, it touches the graph in 2 points at the same time, right? So it only has to do it once, but it would do it in multiple points here. If I were to drag a vertical line across the graph, it would touch our graph in more than one point at a time. So this is not a function. Okay, what about this one? Well, if I had a vertical line, it's only going to touch, again, my lines are not great, but it's only going to touch the graph in one point at a time. So this would be a function. I just want to note, going back to the first graph that we looked at, any diagonal line is going to be a function, because just like this one, no matter what direction our line is slanted, if it's diagonal, if it's a diagonal line, then it's only going, if we pass a vertical line across it, it's only going to touch it in one spot at a time. If it's a horizontal line, it's still going to be a function, because if I were to pass a vertical line across it, it's only going to touch it in one spot at a time. The only type of line that would not pass the vertical line test would be a vertical line, because of course, if I pass the vertical line across it, once I got to the vertical line, then it would be touching it in all points at the same time. So every other line would be a function except for a vertical line. Okay, so we have one more to test. Would this be a function? Nope, because our vertical line will touch it in more than one spot at a time. So this is not a function. Now we're going to determine whether each relation defined y as a function of x and state the domain. So we are trying to determine if this is a function, basically, if y is a function of x. And the way that we do that is we see if for all the values of the domain that we plug in for x, if we can get more than one value of y. Because remember, if we have one x that gives us more than one value of y, if x is paired up with more than one value of y, then it's not a function. Okay, so if we look at this, this is a linear function. The way that we know that it's linear is because we have just x's and y's and there's no powers. So if we have just x's and y's and we don't have any powers, then it's a linear function. Well, we can plug anything in for x in a linear function. We don't have any restrictions. The types of equations that would give us restrictions would be fractions, because we know we can't have 0 in the denominator of a fraction. Other things that we would have restrictions on would be radicals, because we can't have a negative under the radical. But when it's just a plain linear function like this one, we can plug anything in for the domain. So our domain would be from negative infinity to positive infinity. Now, if I were to plug any value in for x, any value, would I get different values for y? The answer is yes. Whatever I plug in for x, if I plugged in 0 for x, then I would get 5 for y. If I plugged in 1 for x, then I would get 2 for y. I would get a different value for y for each x that I plug in to my equation. So this is a function. And like I said before, any linear equation, just like when we were doing the vertical line test, is going to be a function unless it's a vertical line. So if it's just a number equals x, that's the only time when it wouldn't be a function. Any other linear equations would be a function. Okay, let's look at this equation. Well, as you can tell, based on what I said earlier, this is not a linear equation because we have a power on our y value. So let's think about it. First of all, are there any restrictions? Is there anything that I cannot plug in for x? The answer is no. I can plug in any value for x because x is not in the denominator of a fraction and it's not under a radical. So my domain is from negative infinity to positive infinity. Now, is it a function? Are there any values of x that could give me two different values for y? Yes, there are. For example, 4, 2 could be a possible solution to this equation. Excuse me, not 4, 2, 5, 2 could be a possible solution to this equation. Let me show you. So if I had 5 for x and I plugged in 2 for y, and that should be a positive 9, not a negative 9. Okay, I think I have the equation fixed. Okay, so if I plugged into this equation, x plus y squared equals positive 9. I have 5 plus 2 squared is 4, and 5 plus 4 is 9. Okay, so this is a solution to this equation. Okay, what about 5, negative 2? Let's plug that into the equation. 5, and then, of course, anytime we plug in a negative number, we should put it in parentheses. Okay, well, what is negative 2 squared? Positive 4. So this also gives me 9. So this is also a solution to this equation. because 2 squared is 4 and negative 2 squared is also 4. So basically, if my y value is squared, it's not going to be a function. Okay, so this is not a function. Or I can just say no, it's not a function. In this last equation, I do have a fraction. So my domain is going to be restricted because my x value, or my domain, is in the denominator of a fraction. We can't have a 0 in the denominator of a fraction. So anything that would cause the denominator to be 0 has to be restricted from the domain. So what value could I plug in for x that would cause the domain to be, or to cause the denominator to be 0? 2. So 2 is the only value that we can't have in the domain. So the way we would write this is we would say from negative infinity up to 2. 2 is not included, so we use a parenthesis. Remember, bracket would mean that it is included. So up to 2, close it with a parenthesis, unioned with, we're going to pick back up at 2 and go to positive infinity. So this is saying everything except for this number 2 is included in the domain. All right, is it a function? Well, because there are no powers on our x or our y, any value we plug in for x is going to give us a different value for y. So this is a function.